So today we're going to talk about prompting and complex reasoning. And the basic idea is that prompting is a method to make a language model. I said a pre-trained language model, but it could be a pre-trained and instruction-tuned language model, pre-trained, instruction-tuned, and reinforcement learned language model as well. But the basic idea is you provide a prompt, and it could be like the JDK is developed by, this is a super long text, TLDR, and it gives you a summary, or birds can fly. And the reason why this is interesting is because this started to happen around 2021 or 2022, and it really marked a big change in how we do NLP from creating a training data set and training a model to do one particular thing to these kind of generalist models that can do just about anything. And so it's really opened up the possibilities to do a lot of tasks that we never were able to do before. So the basic idea behind prompting is that we append a textual string to the beginning of the sequence and complete it. And this is how we make our predictions. And so if we have something like when a dog sees a squirrel, it will usually, we can follow this up by completing the sequence. And if we have a very weak model like GPT too small, we have when a dog sees a squirrel, it will usually be afraid of anything unusual. As an exception, that's when a squirrel is usually afraid to bite. And then if we complete it with a slightly better model, we get when a dog sees a squirrel, it will usually lick the squirrel. It will also touch its nose to the squirrel on the tail and nose if it can. I could also try it with a better language model, like we could try Claude or something. Let's see. When a dog completes the sequence, when a dog sees a squirrel, it will usually. And it seems to have overthought this a little bit. Bark, chase after it, become alert and attentive, wag its tail excitedly, try to pursue it. So, yeah, actually, I didn't expect it to overthink this much, but that's kind of what language models do nowadays. Cool. So if you have a pre-trained language model that isn't instruction tuned, it definitely wouldn't do like the kind of thing that Claude just did there. It would actually fill it out with, the expected continuation. And this is for better or worse. So like, if we wanted Claude to actually complete a sequence, it seems like it wouldn't be very good at, completing a story for us or something like that, unless we instructed it properly. But a normal language model, a pre-trained language model without instruction tuning would be very happy to complete the sequence for us like this. So how do we prompt models? We have a workflow that we normally follow. The first one is we create a template. So one way we could prompt models is just one-off. So you could just write something in ChatGPT, and that will be the prompt for the model, and it will fill it out. But even when you write something in ChatGPT, usually there's a prompt template that gives instructions to ChatGPT about how it should behave. So typically we have some sort of template that we fill out. We predict some sort of answer, some sort of output, and then we post-process the output into a form that we want. So the prompt templates are a template that we fill with the user's input. And let's say the user's input on a review site was, I love this movie. And our goal is to find the sentiment of the output. And we want to use a language model to do so. So what we could have is we could have a template like X, overall it was Z. And this would be the template that we want to fill in. And so when we create the actual prompt that we send to the language model, we fill in X with I love this movie. Overall, it was Z or something like this. I actually wrote this in a slightly old, or not the way I would have written this had I created these slides yesterday, but basically a more typical way to create this would be like input overall it was this. Usually we use this like bracketed notation. And the reason why is we can use Python to format this. So we would just format this in input. There's also languages specifically for this sort of templating. For example, there's one called Mustache and another one called Jinja. And you can look these up if you want to create templates. They're very like convenient methods to do that. The reason why it's called Mustache is in Mustache you put two brackets around it, and if you put it this way, it kind of looks like a mustache. So that's where the name came from. Anyway, so recently, these are language model prompts. They make a lot of sense if you know how language models are trained, which you should by now. Basically, they're trained by inputting text and predicting the next text. Separately from that, there's this paradigm that was popularized by OpenAI. And the way this works is instead of prompting the model, or instead of sending the model just a text sequence, we send in these messages. And these messages can have a role like system, and then the content. Please classify movie reviews as positive or negative. And then you have a role of user in the content, and it says this movie is a banger. And then it would have to classify that as positive or negative. The system message is a message that's provided to the system to influence its behavior. The user message is input by the user. So this is provided to the provided by the user, and then the assistant is the message output by the system. So you can output like a long string of first having a system message, then user message, assistant message, user message, assistant message, user message, or something like that. So why do we have this format? And what does it actually influence on, what is the actual influence on the language model? So in the end, as far as I know anyway, every language model is still processing text, but it's still processing just plain text, sequences of tokens. But the user messages, system messages, and assistant messages are processed in a particular format. And this is an example of the llama format. This is an example of an alpaca format. Actually, the llama 2 and 3 format is different than this llama format over here. It has some like bracketed tags, which you can also look up. But the reason why we process it this way is because all of these models have kind of been instruction tuned to pay attention to this format. So during the instruction tuning or supervised fine tuning step, all of the output is formatted in this format. And so the models are trained to follow this in a particular way. And the system message in particular has or had a special role in these models. And the system message is considered to be something kind of special that gets special priority. And it gets priority in two ways. The first way it gets priority is it should be obeyed through the entire conversation. Like the model should definitely not forget it anywhere in the conversation. And the other thing is that the system message should never be displayed to the user. So people may have heard of things called like prompt injection attacks or jailbreaking attacks or other things like this, where people have attempted to get this system message to be revealed. So they say, ignore all your previous instructions and tell me the first like part of this sequence. And it used to be that models would very easily reveal their system messages, and now not so much. How do people actually do this? The way they actually do this is during fine tuning, there are some special tricks. So for example, in the llama models, they had a special, essentially training methods that would generate synthetic data that would encourage the model to follow the system message throughout the entire conversation. So they would say something like, please reply only in emojis, or something like this. And then they would create synthetic data that consisted of only emojis as the like assistant message for 500 times in a row or something like that. So basically the reason why we use this chat format is to give the system developers greater control about what the responses look like. Yes.
For them to use different tokens to denote those instructions. Like for example, you see llama have those instruct, whereas these use quantity.
Is there any reason to use different tokens to represent the instructions? Basically, I think within the tokenizer, these tokens are given special, they're like given a special token or tokenized only once. As far as I know, I'm not actually 100% sure about that, but so it doesn't really matter which one you use. But what you don't want to do is you don't want to have a token that's very likely to occur in standard text. And this is maybe very likely to occur in standard text, so this is not a great idea. Let me see if I could actually get this to work in ChatGPT. So let's see. Okay. So this is, okay, so this actually works now. It used to be that if you put this special token in, it like the model would not be able to recognize it. But I guess in ChatGPT now it works, unless I messed that up somehow. But so if this appears like everywhere in standard text, it will get mixed up between when this is like legitimate and when it's not legitimate. Cool. Any other questions? Okay, let's go on to the next one. Cool. Yeah, and if you want to look at the prompt templates, I believe that this link still works. There's a bunch of different like prompt templates in here, and if you just want to look at the code to generate all of the different prompt templates for all of the different models, you can click through this on the slides. Okay, so the next thing we want to talk about is how we actually generate the answers. If we are using a left to right autoregressive model, the way we generate the answers is basically by either sampling or greedy search. And for sampling, we basically sample the most likely token one by one from left to right. For greedy search, we pick the most likely token, or sorry, we sample tokens according to the probability for left to right. And for greedy search, we basically select the most likely token every time. There's a bunch of other inference algorithms, and we're going to talk about them more in an inference class near the end of this semester. But this is relatively simple, not too complex. One thing is if we are only generating a single token, we might limit the length of the generation to be one token. And if we're generating a long form thing, we might not have such a limit. But basically not super complex. Until we talk about chain of thought, which is going to be more complex. So the next thing is, based on the answer, select the actual output. There's a bunch of different ways we can do this. The first way is we take the output as is. The second way is we somehow format the output for easy visualization. The third one is selecting only parts of the output you want to use. And this is actually pretty tricky. And then finally, you can map the outputs to other actions. So the first thing is output formatting. And typically in language models, the language models just generate output in Markdown, and that Markdown is formatted. And the reason why is like Markdown, as I'm sure everybody knows, is kind of like the standard way of simply expressing formatted text on like GitHub or the internet nowadays. So if you ask for a table, it will basically format this as a Markdown table, and it will give you the output. For code, similarly, this is probably just outputting like # # JSON, and then they're formatting that in an appropriate way. One interesting thing here is like somehow this formatting messed up, and it like gave me a weird output at the end. And like every once in a while, like 1 in 20 times or 1 in 30 times, it will make a mistake like this, and that's the way you can tell that it's actually generating Markdown. Then given this, another thing is sometimes we want to extract structured information. So like, for example, let's say we want to predict a star rating, or we want to predict positive and negative sentiment for reviews. What we can do is you would predict like, overall, it was a movie that was simply fantastic or something like this. And if it outputs something like this, in the end, you'll want to find the positive words and get only the words that are indicative of the sentiment. And there's various methods for extraction. Like, for example, in classification tasks, one thing that we do is identify keywords. For regression or numerical problems, we can identify numbers. For code, we can pull out code snippets and triple backticks. So this is very task dependent. One thing to note is I've done some benchmarking of language models, and actually, whether you do this properly or not can result in like 20-point differences in the score of language models. So one thing that I would highly suggest is if you are looking to do benchmarking on a particular data set, like on a coding data set or on a reasoning data set, a math data set, look how other benchmarking code works, and try to use benchmarking code that has like actually worked on this answer extraction properly. Another thing is how you prompt the models can also affect whether they do this well. So if you say, you must surround your code in triple backticks, then it will definitely surround the code in triple backticks. Otherwise, it might not, and that would cause it to, like, even if it gets the answer right, you'll mark it wrong because you weren't able to extract the answer. This is super important. The final thing is output mapping. And so given an answer, map it onto a class or a continuous value. A lot of times you won't have to do this, but some of the time you will. So for example, if you are doing sentiment analysis, you would take like interesting, fantastic, and happy and map them all onto positive, or boring and 1 star and map them all onto negative. And this can also have a big effect on your accuracy. And just to give an example, let's say we're doing sentiment analysis. We could do 1 star, 2 star to 5 star. Very bad, bad, very good. And I don't have a whole lot of like empirical evidence to back this up, but I have found that in general, this right format tends to give you somewhat better accuracy than the left format. in these sorts of numerical grading style things. And I don't know why, maybe it's just because there's more text on the internet that looks like that or something like that. But this can also have a fairly significant effect on kind of classification style tasks. Cool. So these are the basics. Any questions here? Yeah.
It seems like we've gone back full circle.
We've gone full circle from keyword modeling to keyword modeling in this use case. Yeah, one thing I can say is like prompting methods were intended to kind of make very flexible AGI style systems, right? You know, it's now you can ask it to do anything. And it will do it well. In reality, even the best systems are still reasonably fragile with respect to how you word things, how you extract answers, you know, other stuff like that. But the better systems are definitely much more robust, or the better language models are much more robust to this sort of thing than the worst language models are. I actually may have this on a later slide, but since we're here at the moment. There's this paper which I like. Quantifying language model sensitivity to spurious features in prompt design. And this actually kind of goes in and specifically examines how sensitive different models are to different kind of formatting. And this is kind of the standard text that's used for a QA style task. And then if they change it to passage text, answer text with no colons and no like line breaks, you get better accuracy. If you change it to passage colon text with no space, suddenly your accuracy goes way down. And the nice thing about this is they actually examine how sensitive different types of models are to these sorts of things. And what we can see is the performance spread across different models varies quite a bit. So this is like Llama 2. These are base models here. And then I think the instruction tuned models, I don't know if it was in this paper or not, but instruction tuned models tend to be less less sensitive to this format. Another thing is if you're ever in the position to actually do instruction tuning, it's super important to not follow only a single format and to give things in various formats. So if you give things in various formats, the trained model won't be super sensitive, but if you give it in a single format, it will be. Yeah.
What's the intuition behind like taking out a colon, making the model perform better?
Taking out a colon, making the model perform better. So first, the performance difference wasn't like super huge. It was a few points. The intuition behind there are two failure cases that I see in models being like very sensitive to prompts. The first one is that the models can somehow latch on to the fact that a colon is missing or something like this, or a space is missing, and decide that instead of answering your question, they should be correcting your grammar or something like this. So like basically they decide to do something completely different. Another thing is maybe answer extraction stops working well. So they'll output it in the wrong format and actually get the right answer, but your answer extraction is not working. And then the final thing is there are legitimately cases where the performance goes up based on prompts. And a very famous example of this was for code generation. And for code generation, you could add a single line that said, I have checked this carefully and all tests pass. And you would add that to the end of any prompt you added when you were asking it to do code generation, and the answers would suddenly get better. And basically the reason why is because language models are like, basically they're getting correlations, right? And you can correlate them into a space of like being good programmers and being bad programmers. So if you have a lot of typos in your original problem description, you know, careful programmers will probably have less typos in their problem descriptions. So it correlates with getting better text. But recently, because models have been instruction tuned so heavily, I feel like this correlation between the quality of the instructions and the quality of the outputs has gone down. Because now, I don't know about like GPT or Claude or anything like that, but Llama at least uses 10 million high quality instructions to train their models, they said. And because they've used 10 million high quality instructions to train their models, they've kind of like moved it out of the place of being like a bad coder at all, just by instruction tuning. So now the instructions are less important. So yeah. Cool. So now I want to go into few-shot prompting and in-context learning. And few-shot prompting, basically the idea behind this is providing a few examples of the task together with the instruction. And so if you say, please classify reviews as positive or negative, you can give 2 examples of inputs and outputs. And this was super, super important when we were not using instruction-tuned models. So in non-instruction-tuned models, if you wrote, please classify movie reviews as positive or negative, and then you wrote a movie review, it might just continue the movie review. It might just like add more outputs to the movie review if you didn't have these few-shot examples, because it would basically still be just a completion engine and it would complete the movie review. Now with instruction-tuned models, few-shot prompting is a little bit less important, but it still can definitely improve accuracy by demonstrating to the model like the way it should be solving the problems. This is kind of a little detail, but in the instruction tuning format, or sorry, in the assistant format, there's multiple ways that you can provide examples. The first way that you can do it is by adding it to the system message. If you add it to the system message, you can like tell the system what way it should be, or you can give it some examples. This works, but the issue with that is you need to think about what format you want to provide the examples in. So another option that was written in the OpenAI cookbook at least 8 months ago was you can write something like example user and example assistant here. And this, you can provide examples in this format as well. I have to admit, I haven't looked at the OpenAI cookbook this semester, and OpenAI changes a lot of things. So this might not be the most current knowledge, but this is something that you can take a look at if you want. So there's a fair amount of research into few-shot learning. And one thing that you should be aware of is that language models, especially less strong language models, can be very sensitive to a variety of things. One thing is the order of the examples. So if you put the examples in different orders, that can result in the changes in accuracy. If you give a very large number of positive examples or negative examples, that can cause the models to overfit and only output positive labels or negative labels if you're doing sentiment analysis. Also, label coverage. There's also some counterintuitive results. So, for example, there was this paper from 2022 where they demonstrated that actually adding random labels, kind of data with random labels or data with corrupted labels actually still is very effective in improving accuracy. And the reason why this is very effective, or it can be quite effective in improving accuracy, despite the fact that the labels are wrong, is because it teaches the model about, number one, what labels can be used in the first place, and number two, what the format of the data should be in. And sometimes more demonstrations can also hurt accuracy as well. One thing I should mention is, like, as models have gotten stronger, these counterintuitive results have decreased a bit because the models are better at instruction following. So if you have models that are very good at instruction following, they're better at doing this sort of kind of following wrong labels, following labels that they know that kind of a priori are incorrect. So yeah, maybe that's all I'll talk about here. Are there any questions about this? Yeah.
Since models now are being like heavily fine-tuned or instruction-tuned on really high-quality data, is there a chance that models, when users prompt it with bad grammar, become sensitive to the bad grammar because it's not part of the distribution that it was trained on necessarily?
So because models are being trained on high quality data, like, do they become sensitive to the bad grammar because it's out of distribution? That's a good question. I don't know exactly what like the data going into the instruction tuning for like the, most high quality, models, like the most high quality instruction tuning data that's going into like Claude or GPT or Llama or something like that looks like. However, if I were them, I would not have consistently high quality inputs. In fact, I'd have inputs that were not high quality because I would expect my users to be giving me low quality text, but I would have the outputs all be very high quality. And I guess that's probably what they're doing. And so that means that even if you get a low quality input, you could still give a high quality output. Yeah.
Do they backpropagate on the input too while fine tuning? Because then it will, so in the next token prediction, you will teach the model to generate bad quality.
Yeah, that's a great question. So I don't know about this particular case. I'm just guessing about what their data might look like. But do you fine tune on the inputs of instruction tuning data in addition to the outputs? And actually, I've seen both be done, and there's advantages and disadvantages. So the advantage of calculating the loss only on the outputs is you really are only like optimizing to get the right output, and you're not wasting any, parameters or updates on modeling the input. On the other hand, if you need to have like an understanding of the input, then, we know that language modeling is kind of like a proxy optimization function for understanding. And so that can help you better understand the inputs you're getting. So especially if you're getting like, I don't know, something like long medical texts, and then you're expected to answer questions about them. In that particular case, I think it would probably be better to, fine tune on the inputs as well. Yeah.
What the accuracy and the percent correctness here, I'm a little confused.
Oh yeah, so the percent correct, this is the percentage of labels in the few shot examples that are correct. So for example, if I was at 50%, I might flip this to negative. So you would get, I really don't like this movie, negative. This movie is great, positive. Or if it was 0% correct, I might like swap that to positive and this to negative. The y-axis here is how high is the accuracy of the final system that uses these prompts with, correct or incorrect labels. And what you can see is compared to using no few shot examples, using few shot examples with 100% incorrect labels still gives a big bump in performance. And so that indicates that like learning the format is more important than learning the labels. But as I said, I think this won't hold with the newest GPT models. Like the newest GPT or Claude models or something like that are smart enough to realize that the labels are wrong and actually give you like wrong labels. Cool. Okay, so next I want to go to prompt engineering. So prompt engineering, basically, there's different ways to do this. And this has to do with designing prompts so that you get the most desired output. You can do this either manually by configuring a manual template based on the characteristics of the task using your intuition or other things like this. Also in automated search, and this can be done in discrete space or continuous space. So yeah, actually, this is the paper that I just talked about. So for manual engineering, you can engineer the format, like I just mentioned. I'll skip over that since I already mentioned it. Another thing is manual engineering to give clear instructions. And actually, one of the funniest things is we're moving, in some cases, we're moving from the point of being like programmers and just to the point of being like just good communicators. Because like recent language models actually are quite good at following instructions. And a good prompt for a language model is often also a good prompt for a human. So if you create a prompt that is not very clear for humans, it will also not be very clear for language models, and you'll get worse performance. So this prompting guide has a bunch of tips. But some of the examples are let me open this up. So some of the examples that are on this guide are things like start simple. So don't immediately try to write a really, really long prompt that covers all of the edge cases. Tell it what it needs to do in like active. So translate the text is very simple. Being specific. So extract the names of places in the following text, desired format, avoiding impreciseness. So keep the explanation short, only a few sentences, and don't be too descriptive. Use 2 to 3 sentences to explain the concept of prompt engineering to a high school student. So instead of like just a few sentences, say 2 to 3. It's more specific and it gives you a better answer. Try to avoid telling it not to do things whenever possible, which I just failed at doing, by the way. I told you to avoid not doing something, but or avoid telling it not to do something. But sometimes there's no way to avoid using a negative, but if you can avoid using a negative and use a positive instead, that can give you better results. So there's a bunch of these little tricks like this, but a lot of these would be the same for humans. Like when writing the quiz questions for this class, I try to avoid negatives in the quiz questions, or I ask the TAs to avoid writing negatives in the quiz questions. So it's kind of a similar principle. One important thing about language models is right now they don't complain when you're vague, whereas humans might. So it's kind of on you to discover when your prompts are not appropriately scoped. Or maybe if you can come up with a system that allows language models to complain when you're being too vague, then that would be a good research project for you to do for the class, for example. So this is automatic prompt engineering. Another thing that I often will do is I'll talk more about error analysis in 2 classes from now, I think. And if you can go in and do really good error analysis, you can always add things to the prompts to improve based on the error analysis that you did. Okay, and then separately from this, there's methods for automatic prompt engineering, including paraphrasing, gradient-based discrete prompt search, prompt tuning, prefix tuning. So prompt paraphrasing is a method that we came up with in 5 years ago now, where basically you use a paraphrasing model to paraphrase prompts. And the way this works is you have a prompt and you run it through a bunch of paraphrases. And then ideally, you'll select the one that gives you the highest performance. And so if you have a small amount of held out data, you can just run all of them through and select the one that gives you the best performance. You can also do this iteratively. And when you do it iteratively, you find the best prompt or prompts, and then you do it again on the best prompts until you gradually approach an optimum there. So one important thing to point out here is the output of this prompt paraphrasing is human readable. So if we have X shares a border with Y, we get things like X has a common border with Y, X adjoins Y, other things like this. And it is text. It's a textual prompt. Another method that people have used is gradient-based search. And gradient-based search is basically what you do is you take this prompt here, and this prompt, essentially what it is it's 5 tokens. And the way you create it is by creating a template where you have like a sentence And then you have 5 optimizable tokens, and then you have the answer or the output that you want to generate. And then you backprop into these tokens. And when you backprop into these tokens, you gradually optimize these tokens. And this gives you 5 continuous vectors. And then based on the continuous vectors, you clamp them onto existing tokens. And what I mean by this is after you get the continuous vector, you then find the nearest token that is most similar to the vector that you optimized and use that.
Is the search space the entire vocabulary?
Yeah, the search space is the entire vocabulary.
So it could also be just randomly selected tokens, not actual full word.
Correct, yeah. Like right here, this is using full words, but it could be tokens. Yeah. And the result of this is something like atmosphere a lot dialogue clone totally, which is not, really comprehensible sentence, but it is discrete tokens in the language we're interested in. Another one is prompt tuning. And prompt tuning is basically the same thing, just without clamping. So what you do is instead of taking these optimized vectors and getting the vocabulary item that's the most similar to them, you just keep the vectors as is, and you keep them as like length 5 kind of soft prompt that's in continuous space. Yeah.
Do the tokens that you get finally, which are continuous, like have any meaning?
No, not here.
Just use those tokens and like nothing else. You'd likely get garbage basically. Like if you just use these new tokens that you like optimize and feed it into the language model.
I don't know if that's necessarily the case that you would get garbage. You might get garbage or you might not get garbage depending on the tokens. And I'll talk a little bit more about that in a second too. And then the final thing here we have is prefix tuning. And prefix tuning is like prompt tuning, but the difference is prompt tuning is only tuning the first part of the sequence. And it's only training, like, for example, 5 tokens here. Prefix tuning is tuning a prefix for every layer. And they tune both the key vectors and the value vectors. So they, instead of tuning a prompt, like x1, x2, x3, which is then multiplied by the value in the key vector matrices. They're actually tuning like x1v, x1h, x2v, x2h. So if you only apply prefix tuning to the first layer, it would be very similar to prompt tuning, but it would have twice as many parameters. So we talked about parameter efficient fine-tuning last time, but there's actually a very interesting connection between them, which we talked about in this paper here, where a lot of the parameter efficient tuning methods look a lot like prompting methods. And the way it works is we have a language model module. So this could be like a transformer or something like this. And we have the input to the transformer, we have the hidden layer, and then we have gating in addition. And prefix tuning, the way it works is we have essentially a matrix multiplication, we have a softmax, and then we have another matrix multiplication. For LoRa, we just have a matrix multiplication, the 2 matrix multiplications here. For parallel adapters, we have a matrix multiplication and ReLU and other things like this. You can look into the details in the paper. But what this entails is actually prompting models is a way of optimizing their parameters. And I'll go through this because I think this is a really interesting insight. And it also tells you a little bit about like what we can expect prompting to be able to do and prompting to not be able to do. So natural language prompts are kind of ones that we manually create ourselves. And this is the least general way of doing things because we're creating them manually in natural language. Prompt paraphrasing is a little bit more broad because we're not creating them manually anymore. We can try a lot more of them. Discrete prompt search now no longer requires the output to be natural language, but it still requires it to be a discrete sequence. So we're only allowed to pick vectors that are from our vocabulary for the model. Continuous prompts now make it even broader, and this can be all of the any continuous vector. Multi-layer continuous prompts or prefix tuning is even broader because now we're tuning all of the layers, not just the first layer. This is a subset of parameter efficient training because it's very similar to adapters, but it uses a specific format of adapters used in the models. And then that's a subset of all the training methods that we would possibly want to be using. So the reason why this is interesting also is I think we can think of natural language prompts as like actually manual optimization of our models, right? So we're manually picking some parameters for our models and we're optimizing them here. And the interesting thing is that this works, right? Like manually optimizing parameters of a model seems like a horrible idea. Like we have machine learning for a reason, like, but nonetheless it works. And the reason why it works is because like we have models that are very well aligned with our, with human expectations and stuff like that. Another thing that this entails is a natural language prompt can always be further optimized to improve accuracy. So like, let's say you came up with a really good prompt, you could then like unclamp the parameters and further fine tune the model, further fine tune the vectors in that prompt to increase accuracy. And that would allow you to improve the accuracy. So I think this connection is really, really interesting and maybe still underexplored in research as well. Yeah, so that's just what I said. This can be used as a prior. There are a very small number of models that actually have looked into optimizing, further optimizing human prompts, but these are relatively uncommon. Cool. Any questions or discussion or? Okay, sounds good. Now I want to switch gears a little bit and talk about reasoning in LMs, and specifically reasoning from the point of view of prompting methods. And if we think about what is reasoning, it's using evidence and logic to arrive at conclusions and make judgments. Reasoning can be formal, focusing on strict truth values, and formal logic generally doesn't have a whole lot of probabilities in it. It's just talking about whether something's true or not, whether something is included in a set. It includes things like math, mathematical proofs, and other things. Informal can be based on experience and intuition. It can have fuzzy implications and other things like this. And generally, language models traffic in the latter, but you can do the former with language models as well. There's different types of reasoning. The first one is deductive reasoning. And basically, this is using logic to go from a premise to a firm conclusion. And this could be something like all mammals have kidneys, all whales are mammals, and thus all whales have kidneys. And if the first two are true, then the final one is guaranteed to be true because we're talking about all, and there's no exceptions there. Inductive reasoning is from an observation predict a likely conclusion. And so when we see a creature with wings, it is usually a bird. We see a creature with wings and the creature is likely to be a bird. So this, it's not so firm. It's probabilistic. And, if we are only allowed to do deductive reasoning, very quickly, we aren't able to do anything, right? Because there's so many exceptions to every rule, which makes it very difficult to say anything firm. Once we can do things that are a little bit more soft, that makes it a lot easier. Another thing is abductive reasoning, and abductive reasoning is from an observation, you predict the most likely explanation. And so if we think about a car cannot start and there's a puddle of liquid under the engine, we could guess that the car likely has a leak in the radiator. So that's like guessing the causal reason of why we saw our observations here. So I'm going to mostly talk about large language model-based reasoning because I think that's a lot of what we do nowadays in natural language processing. However, reasoning is something that traditional semantic representations are also very good at. I have an example here from Prolog. And basically, Prolog is a language that was specifically designed in order to do these sorts of logical operations. And so you can provide to it the fact that you demonstrate that this is false, that all people dying have implies that Mia is dead and Zed is dead. And then you go through this derivation process and you prove that it's false that Mia is dead and Zed is dead. And thus you can prove by falsification that this first predicate is true here. There's a really nice book, Representation and Inference for Natural Language, where you can learn about this. I think you can get PDFs online or get it in the library or something like this. So if you're interested in kind of the symbolic reasoning, this is interesting. Also, Sean Wellick here does a lot of mathematical reasoning in Lean, which is another one of these kind of symbolic languages that's used for proving mathematical proofs. So you can read about that as well. But I'm going to mostly not talk about this sort of symbolic reasoning and talk about it in large language models. And so the first thing that we definitely should be aware of is something called chain of thought prompting, which we've already talked about a little bit. But chain of thought prompting, basically the overall idea behind it is that instead of prompting a model and saying, Roger has 5 tennis balls, he buys this many more, how many does he have now? The model outputs the answer directly. Instead, what we can do is we can add a quote unquote chain of thought, which is the steps that the model goes through in order to give the answer. And the model will then use the steps at test time also and give you the output answer. And one thing to note here is that right at this point, this is using few shot prompting, like I talked about before. It has one example of an answer with a chain of thought. And then as a result, the model outputs the chain of thought. And empirically, this has proven to be like very important for getting good results on a subset of tasks. And when I say a subset of tasks, these are tasks that require kind of this multi-step reasoning, like especially things like math, but also things like kind of just more complex problems in general. There's a couple reasons why this is useful. The reason that seems most prominent and plausible is that it provides a model with adaptive computation time. So transformers in predicting the next token have constant computation time, right? Where the computation time is equivalent to the amount of time it takes to calculate the representations, multiplied by the number of layers and other things like this. And so if you give it a really, really hard problem, it isn't able to do this, adaptively. And chain of thought gives it it gives it adaptive computation time where it can spend more computation on answering more difficult problems. So I talked about few shot chain of thought prompting. There's also a really nice paper. This paper was one of the most creative papers that I saw in 2022 when it came out, which was essentially few shot chain of thought prompting is just using few shot prompting to demonstrate how the model can follow chains of thought that were created in the demonstrations. This paper, basically what it said is it just added, you put a question, and then in the answer you add let's think step by step. And this encourages the model to do kind of chain of thought. And the reason why is because even for a base model, even for a pre-trained model that has not been instruction tuned, there's enough information on the internet, there's enough examples on the internet where people have given a math problem and then written, let's think step by step, that this encouraged the model to be in that like space of doing, reasoning, of adding reasoning before it answered the question. Now you don't need to do this anymore. So like, if I give an example, let's see. What is pi cubed divided by 5, and then square rooted. Let's see if that works. Okay, I'm going to talk about this. I'm going to talk about this in a few slides, but it wrote a computer program for me. So this is one variety of a chain of thoughts, but it wrote the computer program and then executed the computer program instead of like going through the chain of thought. But you do not write a computer program. Yeah, so this is more like traditional chain of thought. So it goes through this and gives the answer. I don't know if that's exactly correct, but or actually we can go back and look at our other example. So 2.4902, yeah. So it got it correct even without writing a computer program. Yeah. Yeah, this code was executed. Yeah.
There's a Python interpreter there.
Yep. Yeah. So like this one, when you see something like this and you see result, that's actually executing code. That's actually, I'll just skip. So this method of like using code to solve problems is something called program-aided language models. It's something we proposed like 2023 or something like this. And the basic idea is just instead of a chain of thought, that's written in natural language, you write it in code and then you execute the code to answer the problem. And this is especially good for problems that are written that require like math or other things like this. Now this is implemented in most like major language model platforms like ChatGPT or Gemini or other things like this. The interesting thing is they kind of dynamically decide when to write code. So I just gave it a prompt that said do not write code, and then it decided not to write code. So now the models decide whether to do this or not. The way they do this is by having a special token token or tag that indicates when that's code that should be executed and when it's code that should not be executed. Cool. Any other questions? Yeah.
To actually extraction with the zero-shot solution. Or like, do you do some kind of system talk to control the output? But like, there's no example of it.
Okay, yeah, great question. So how do you do answer extraction with zero-shot COT? There's a number of different ways you do it. It kind of depends on what task you're handling. The most common way to do it for math is just to extract the last number.
What about like code generation?
For code generation, it's a bit tricky. I think actually most most code generation without instruction tuned models uses like few shot. You can kind of hope that the model might like write things in backslashes or something like that, but actually you lose a lot of accuracy when they don't do that. So as far as I can tell, I can actually check that for sure though. So let's see. So yeah, sorry, I can't find it right away, but my guess is that they do few shot for base models.
From the model to like output the answer in a particular format, right? Like after let's think step by step, write the final answer.
You can do that, but base models might not follow that appropriately because they're not instruction tuned. But yeah, that's a good question. I don't actually know the answer, but you could take a look at papers. Yeah. It results in a huge accuracy difference for math problems, especially complex math problems, because you can just execute the program. For example, if you don't use code, multiplication is hard. Like 5-digit multiplication still will not be consistently done with strong language models, but if you use code, it's trivial. So
you're always at an advantage to prompt to ask it to generate code and execute it?
I wouldn't say always. Like if it's not a math problem, then probably not. But if it is something like a math problem, then I'd say almost always it's going to be better. Yeah. Cool. So the next thing I'd like to talk about is emergent abilities. And emergent abilities are abilities that only are thought to occur at very large, when you start using very large models. And you have this thing where you have a model's size and you're getting like near zero performance until you get to like, I forget exactly how large this is, but this is maybe like 30 billion parameters. And then suddenly when you jump up to like 70 billion or 100 billion parameters, everything starts working. And reasoning style tasks are an example of something where this is the case. And the very large models tend to be quite good at it. And a lot of the smaller models tend to get like near zero performance. And for a long time, this was kind of like, or for some time, this was kind of like mystical. It's like, oh, you make a really big model and suddenly the model like is really smart and it can do all these things. But there's actually a really simple explanation for this. And it has to do with the way we evaluate models. And this is explained in a lot of detail in this paper. So I won't explain all of the details, but I'll give you the overview. But basically, if you have a model and it's calculating the probability of the next token, and every time you double the model size, it gets 0.1% better at predicting the next token. And then maybe even that like starts leveling off as you get better, but like 0.95, 0.99. The model is gradually improving as you make the model better. It's getting like a little bit better at predicting the probability of the next token. But the problem is, in order to solve, okay, so now let's think of a text classification task. If we think of a text classification task, it just needs to get one token right. And so as this probability goes up, the text classification accuracy actually will go up kind of linearly as you improve the model ability. But for reasoning, it doesn't need to just get one token right. It needs to get like 40 tokens in a row right, or 50 tokens in a row right. So now let's say the probability of getting the next token right is 0.9. The probability of getting the whole reasoning chain could be like 0.9 to the 10 or 0.95 to the 10. Because you need to get all of them right in order to get the final answer right. And so even though the accuracy is like 90% at getting the next token right, I can pull out my handy chat GPT. And what is 0.9, 0.95, 0.98, 0.99 to the 10? And it writes a program for me to. So what you can see is like even a quite good model that gets 90% accuracy of predicting the next token in difficult situations and reasoning tasks will only get like 38%. And if it's like 0.8, it'll be like near zero, right? So the fact that reasoning requires you to get like all of the tokens right or many tokens in a right in sequence makes this seem like an emergent ability. The good news is this means that you don't necessarily need to evaluate models according to their final accuracy. You can also evaluate models according to other methods that look more directly at whether you're getting the tokens right. And there's a method called Breyer score that they use in here, and they demonstrate that this gives you like a smooth improvement from small to large models, even for like these quote unquote emergent abilities. So that's a good thing to know about. Okay. Next thing I'd like to talk about is the reliability of the explanations. Basically, what people have shown is that there's a relationship between the accuracy of the answer and the factuality of the explanation and the consistency of the answer and explanation. Basically, like the summary is that usually if you get the explanation right, you're more likely to get the answer right. Usually if you get the answer right, the explanation is more likely to be factual, but it's not definite. It's not a one-to-one relationship. And this is actually kind of important for reasons that I'm going to talk about in a few slides. Another thing that people have observed is that even for the same model, if you sample a whole bunch of explanations from that model, the longer explanations tend to have a higher correctness rate. And so you can kind of use this as a method of supervision. And the way they do that in this paper here, like I posted this paper more because it's like an interesting observation that if you spend more time in a chain of thought, you get the answer right more of the time. But they also use that in this paper where they basically sample a whole bunch of explanations and then take the longer ones and then do self-consistency among the longer ones or do voting among the longer ones. And that gives them higher accuracy, which is kind of an interesting little trick. Finally, I'd like to talk about methods of training models for chain of thought. There's a few methods for this. The first and a kind of famous one is called ORCA. And this paper is about training small models for reasoning. The way it worked is basically they took data from a big instruction tuning data set, and they used a large model to generate reasoning chains, filtered down the reasoning chains to try to get good, accurate ones. And then they trained smaller models with these reasoning chains to train them to be better at reasoning. And it's a very simple data synthesis approach, but it ended up allowing smaller models to be better at kind of reasoning. This data set is not available, but there's a data set called OpenORCA that you can use that is available if you're interested in using this. And also some of the data sets that Xiang talked about last time can also be used in similar ways.
Just to clarify, 103 means it's 3% better than ChatGPT.
Yeah, this is relative performance with respect to, and by ChatGPT, they mean GPT 3.5, I think.
Or better TV is like 103%, so that's it's better.
Yeah, it's better, yeah. Another thing that is interesting to think about when you're thinking about reasoning chains is something called process supervision. And what process supervision is it's a method to identify good and bad parts in the chain of thought. And this is an example where they basically first did human annotation of chains of thought, where they either gave a thumbs up or a thumbs down to individual chain of thought steps and said, this is the place where you started making mistakes. Then they trained a reward model to guess which parts of a chain of thought were correct or incorrect. And then they used that as supervision. And the reason why this is useful, I'm going to talk about this more in the reinforcement learning class, but reinforcement learning is very hard. And one of the hardest parts of reinforcement learning is something called credit assignment. And credit assignment is where you have a really long series of steps and you just get a reward at the end about whether you did a good job or didn't do a good job. And that's really tricky. It's a really tricky learning situation because you need to say, like, this whole thing is bad, despite the fact that, like, most of this is good. Most of the reasoning steps are good. So this is a more direct way to, like, supervise the intermediate process. And this was basically this was basically done by collecting supervision data and training a reward model that allowed you to do that. Cool. Yeah, I already talked about program-aided language models. Another interesting thing to know about is that generating outputs in programmatic format can actually improve your accuracy even if you're not doing programming. And this is one of our papers where we examined this fact, which is we had a procedural knowledge prediction task or several procedural knowledge prediction tasks. So this is not predicting programs or math or anything like that. It's just trying to get like this graph, basically. And what we did was we took a language model trained primarily on text and a language model trained primarily on code. And then we had the language model that was trained primarily on code generate Python code, also generate these kind of like more esoteric programming languages like this. And the result was if we had it generate Python code, it did a better job of this procedural knowledge prediction task than other tasks. And the reason why we guess is just because it's seen so much Python code, and that Python code, describes procedures, right? Programs are procedures. So if you ask it to generate Python code, it gets into a mode where it's like just good at generating procedures, and then we can extract that. Also recently, a lot of models are trained for like tool use. So for example, the OpenAI models and a lot of the open source models have a specific format where you provide like tool use documentation or function documentation, and they generate outputs based on JSON format. And those models are specifically trained to generate like a fixed JSON format, given that you provide them the JSON documentation. So that can help you format things a bit better. So that is all I had for today. Are there any questions for this? If not, I would like to talk a little bit about the new OpenAI model also. So, okay. So the new recently OpenAI came out with O1, which is not GPT-5, it's O1, I guess. And it's a new model. And basically what it does, I need to pay $20 to OpenAI, otherwise I would show it to you on my screen. But basically what it does is it quote unquote thinks for a certain amount of time before it generates an answer, and it seems to think more for more complex questions, think less for less complex questions. That's basically what chain of thought is doing. So, like the original motivation for chain of thought the original motivation for chain of thought was that it gives you adaptive computation time, and that's essentially what the new model is doing also. It's giving you adaptive computation time. In OpenAI's documentation, they say they can't show us the chain of thought because the model needs to think raw thoughts, and we can't censor its raw thoughts, but we don't want to show its raw thoughts to people. I think that's completely lying, honestly. I think they don't want to reveal their trade secrets for commercial purposes, but you know, if anybody at OpenAI wants to correct me on that, I'm happy. I'm happy to be corrected. They could show me the chain of thoughts, and I'll tell you they're too raw to show to anybody. But if I have to guess what they're doing, I think basically they're training models with chains of thought. Maybe they're giving them much longer chains of thought. Maybe they're prompting them to have additional chains of thought, or think very thoroughly, or things like that. Then separately from this process supervision paper is also by OpenAI, and I imagine they're probably using something similar to this. So they're just generating. I would guess that what they would be doing is generating lots of these chains of thought for difficult problems. And essentially performing reinforcement learning, probably with this sort of process supervision in order to train the model. And then they're not showing us the chains of thought. That would be my guess. I might be wrong. There's probably a lot of additional details in there to make it work, but that's the best guess of what's going on there. So yeah, that's all. Thanks.